Okay, so this is chapter 10, problem number 3 of the end of the chapter problems. And this problem tells us, consider the following reaction in an aqueous solution. So we have 5 bromines plus a bromate plus 6 hydrogens react to give us 3 diatomic bromines plus 3 H2Os. At any given moment during the reaction, the rate of disappearance of bromine is 3.5 times 10 to the negative 4 moles per liter per second. What is the rate of appearance of bromine? What is the rate of disappearance of hydrogen? And then what is the rate of reaction? So what we're going to do here is we're going to determine the appearance of the bromine, the diatomic bromine, and we're going to be able to find the disappearance of hydrogen. And finding those values, we're going to be able to calculate to determine the rate of the reaction. So obviously what we're going to need to do first is we need to calculate A and B. So what I'm going to do first is I'm going to take a little bit of space and erase. I'm going to erase this little bit here, and then we'll go back and fill in the questions. Okay, so the first part, it says, what is the appearance of diatomic bromine? Okay, so why is it an appearance? Because if we look at this reaction, of course, for equilibrium to take place, the rate is going to go up on the product side and come down on the reactant side. So this is a reactants over here on this end, and this is our products. So, of course, when we see the word appearance, we're talking about the concentration going up on the product end. So that's why it's asking the rate of appearance for diatomic bromine. So we're going to use this value that we've got here for the rate of disappearance for our bromine, which is this guy right here. And we're going to use that to compare with the rate of appearance for our diatomic bromine on the other side. So what do we know? So we know that the rate of disappearance is 3.5 times 10 to the negative 4 moles per liter per second. Another way we could call this is 3.5 times 10 to the negative 4 molarity per second. But we'll stick with this moles per liter per second since that's how the question's being asked. And this is for just bromine by itself. Okay. Now let's look at the coefficients out front of our two elements in question. We notice bromine, for every 5 bromines produced in this reaction, we create 3 diatomic bromines in the products. So I can convert, using a little bit of conversion, I can convert this 3.5 times to the negative 4 moles per liter per second of bromine in terms of moles per liter per second and diatomic bromine. In order to do so, I'm going to need to convert. So I'll create a little conversion table. So we see that for every 5 moles of bromine, notice I'm putting it in the denominator because, again, I have to cancel it, and up here it's in the numerator. For every 5 moles of that, I'm going to get 3 moles of diatomic bromine. Okay, so now we can just cancel these out, get rid of the moles as well. And notice I'm going to have moles per liter per second again, because there's the mole and then there's liters per second. Now we just need to calculate this 3.5 times 10 to the negative 4 times 3, and divide that by 5. And what I get here for a final value is 2.1 times 10 to the negative 4 moles per liter per second of diatomic bromine. So this is the answer to part A. Okay, so what I'm going to do is I'm going to keep this up here on the, just see if I can't size this down. And we're going to keep this for future reference. So let's scoot it up and see if I can't squeeze it down. There we go. Scoot this up here. Now let's go ahead and try the second part. Now remember what part B was what was the rate of disappearance of H? So the hydrogen, notice it's a reactant. So that's why we're asking for the rate of disappearance, because again, for this reaction to occur, disappearance needs to take effect on the reactant side for appearance to take effect on the product side. So now we're going to use the same concept. We know that we have the rate of disappearance for bromine is 3.5 times 10 to the negative 4. And for this reaction to occur, for every 5 moles of bromine we need to have 6 moles of hydrogen. So now we're going to use that for our conversion table. So again, the 5 moles of bromine are going to come down below here. And we're going to have 6 moles of hydrogen up here. Now we can see that we're going to get rid of our moles of bromine again. And this time we're going to multiply. And again, we're going to get a mole over liters per second. Again, this is like molarity per second. And let's determine what we've got here. 3.5 times 10 to the 4 times 6 divided by 5 is going to give me a value of 4.2 times 10 to the negative 4 moles per liter per second. Now notice this value is double the amount for Br2 or diatomic bromine. And that makes sense because we have 6 hydrogen atoms and 3 diatomic bromines. And that because of that, it's double. So obviously the concentration is going to be double, or the rate of disappearance is going to be double compared. So let me go ahead now and select this. We're going to size this over. Whoops, that's not what I meant to do. So now that we've got the solution to this, we can go ahead and solve for part C. Now remember, part C is going to ask us what the rate of the reaction actually is. So how do we find that? Well, I'm just going to keep that like the way it is. So now we're going to find the rate of the reaction. So now let's get rid of this information. So rate of the reaction, the basic idea of the rate of reaction is this. The rate is equal to, if we have A plus B equals C plus D, how we would write our rate of reaction is simply 1 over A times the rate of A, big A, which is equal to 1 over lowercase b times the rate of big B, which is equal to 1 over C times the rate of big C, which is equal to 1 over little d times the rate of big D. So we've got 3 of our 6 or 5 up here. Now notice we didn't use H2O and we didn't use bromine, but we can find those two doing the same concept. Now, let's find out if indeed, let's call our A bromine. Let's let our B equal diatomic bromine, and let's our C equal hydrogen. And let's find out if these do indeed match. So let's first try with bromine. So we know if this is bromine, this is 5. And then the concentration of bromine is this guy right here. So let's find out. So for the rate, it's going to equal 1/5 times 3.5 times 10 to the negative 4 moles per liter per second. And whenever we calculate this, we get a final value of 7 times 10 to the negative 5 moles per liter per second. Okay, so there's the rate for that. Let's try the rate for diatomic bromine. Notice the diatomic bromine had 3 in front, so we're going to divide that by 3, and we're going to multiply it by the rate of appearance that we found. So that's going to be 2.1 times 10 to the negative 4 moles per liter per second. And when you calculate this, you're also going to get 7 times 10 to the negative 5 moles per liter per second. And just for good measure, let's go ahead and try this hydrogen one as well. So let me just erase this here. And when we try our hydrogen here, again, we're going to divide by its coefficient, so 1/6, and we're going to multiply by the rate of disappearance this time, so 4.2 times 10 to the negative 4 moles per liter per second. And when we calculate it, again, we're going to get 7 times 10 to the negative 5 moles per liter per second. So what is our rate? Well, it's obviously going to equal 7 times 10 to the negative 5 moles per liter per second. And this is going to be the final answer. So again, we used the information we found. Theoretically, we could have just went with the very first, just by reading this question, I could have went directly to part C to answer the final answer. You know, I could have went directly to part C without having to solve parts A and B. But in solving parts A and B, we were able to confirm that our rate was indeed that amount, that it does match for all 3 that we calculated. So indeed, we did get the correct answer.